The next talk is GAL, Geometric Adversarial Loss for Single View 3D Object Reconstruction. And the authors are Jiang, Xiaojuan, Shaoshuai Shi, and Jiaya. And the talk will be given by Li.
Hello everyone, I'm Jiang from the Chinese University of Hong Kong. Here my presentation is about single-view 3D object reconstruction. So first, what is single-view 3D reconstruction? Given only one input color image, single-view 3D reconstruction is a process of reconstructing the complete 3D model of object according to the input image. 3D reconstruction could be widely applied in 3D printing, robotics, virtual reality, and augmented reality. Usually, there are two types of representations for 3D objects used in previous approaches for 3D reconstruction. The first is voxel-based representation, which requires the network to directly predict the occupancy of each voxel. Voxel-based representation could be easily integrated into deep neural networks. The second is point-based representation, in which the reconstructed object is composed of discrete points. This kind of representation is more scalable and flexible. Point set generation network is a pioneer work to utilize point representation for 3D reconstruction. The network is composed of several encoder-decoder hourglass modules and a fully connected branch. It's responsible for generating point locations that maps input image to its corresponding point cloud. Chamfer distances are designed to measure the distance between prediction point set and ground truth set. With chamfer distance as loss function, the generator could predict a reasonable point cloud according to the input image, but they do not consider the shape of the object from a global perspective. The part of the object with less points contributing to it, like the wing and the tail of the airplane, may have distortion in the reconstructed result. To resolve the problems, we build our framework on top of the point set generation network and propose a supplementary global constraint loss. We call it geometric adversarial loss. It consists of a multi-view geometric loss which tries to constrain the global shape of the object, and an adversarial loss which constrains the object in a global semantics way. Our proposed framework could further improve the quality of the predicted point cloud. Let's see these images. When measured using chamfer distance, baseline and the hours result are similar, especially in this case. However, it's obvious that the baseline reconstruction quality is lower than ours. It's because that chamfer distance does not consider the global geometry and only point-to-point constraint is adopted. Our geometric adversarial loss serves as a global constraint. Now, I'll introduce the geometric adversarial loss in detail, which is a major component in our framework that introduces our global constraint. First, for a 3D model, we want to enforce it to follow the 3D geometry by a multi-view geometric loss. We know that humans could obtain the knowledge of 3D shape of an object by the experience of seeing such kind of objects from different views, and thus humans could naturally complete the 3D shape when only one view is available. Our model follows such insight. To be more specific, we design a multi-view geometric loss, which tries to let the network learn the shape of an object from different views. First, we project the 3D point cloud to an image. For each point in the point cloud, we transform point with 3D world coordinate to camera coordinates and then project them to the image plane. R and D here represent the rotation and translation parameters of the camera regarding the world coordinate. We change R and D for changing the camera view. K is the camera intrinsic matrix. The intrinsic parameters of our artificially created view camera are well set to guarantee that the object is completely included in the image plane. We synthesize view-related images according to the projection function and then consider their geometric consistency. However, we could see in these synthesized images that they are with different densities. There's another example of density difference. The projection images from ground truth is much denser than our corresponding prediction. To resolve the discrepancy, multi-view geometric consistency loss is added in multiple resolutions. In the low-resolution mode, the density difference of 3D point cloud will not be reflected in projected images. In high-resolution mode, we set height and width of image plane to large values. Images in this mode could contain more details of the object, but different in valid pixel density. Thus, we only check the valid pixel of predicted image to see whether there's a valid pixel in the neighborhood of the corresponding pixel in ground truth image. This enforces the predicted points to lie in the manifold of ground truth 3D model. However, this is a single directional constraint. We also want to ensure that the predicted points fill the whole shape of the ground truth model. Thus, in low resolution mode, where we set height and width of image plane to small values, we add a bidirectional geometric constraints to keep geometry consistency, although details are lost in low resolution. Rough shape is still visible and can be used to check the consistency. Our multi-view geometric loss is defined as a sum of low resolution loss and the high resolution loss. Besides the multi-view geometric constraints, we also propose to use point-based conditional adversarial loss to constrain the 3D geometry in a semantics way. We design a discriminator to handle point data. Point net is applied to extract features of the generated and the ground truth point clouds. Besides, the discriminator could better distinguish between the real and the generated fake samples with the 2D semantic feature provided by the original image. Thus, the RGB image of the object is also fed into the discriminator as a guidance. We use a pre-trained VGG classification network to extract 2D features. The 2D features are then concatenated with the 3D features produced by the point net for identifying real and fake samples. For the computation of adversarial loss, we apply LS-GAN, which replaces cross-entropy loss function with least squared loss. For positive samples, which is a real 3D model along with input image, discriminator tries to classify it as true sample. And for negative samples, which are generated 3D points with input image, discriminator tries to classify it as false sample. Contrarily, the generator tries to generate a point cloud that could cheat the discriminator so that it could be classified as true by the discriminator. The total objective tries to constrain the predicted 3D point cloud in both global and local way. We combine the conditional adversary loss and the geometric consistency loss as GAL for global regularization. We also use chamfer distance to measure the point-to-point similarity of 2-point sets as a local constraint. The generator and the discriminator are optimized alternately during the training process. Next, I'll show some experimental results. We perform our experiments among different methods on the ShapeNet dataset, which is a large collection of textured CAD models. The performance is evaluated with the point cloud-based chamfer distance, voxel-based intersection over union, and the 2D projection intersection over union. We could see in this table that the final GAL model could outperform the baseline in this 3 evaluation metric. Here's the qualitative results from different methods. Baseline predicts less accurate structure where shape distortion arises, such as the lag of chairs and the connection between two objects. On the contrary, our method can handle these challenges and show better results. Here is the comparison between the trivial generative model and our model with multi-view geometric constraints. As we can see, when observed from the input image view, baseline seems to be comparable with our result. However, when the viewpoint changes, the baseline result could not fit the geometry of the object. In contrast, our reconstructed point cloud is still consistent with the real object. That is because with multi-view geometric loss, the network penalizes incorrect geometric appearance from different views. There's also some comparison between baseline and our model with conditional adversary loss. Adversary loss helps explore the semantic information and produce plausible 3D object models. Without adversary loss, the generated point clouds seem unnatural, while ours look more realistic from different views. For example, the chair generated with only chamfer distance loss obviously cannot be recognized as a chair, especially when observing from the side view, while our results have much better appearance. Here are also some real-world examples. To conclude this talk, we designed a geometric adversary loss, which improves the reconstruction quality in a global way. That's all of my talk. Thank you for your listening.
Okay, I see an audience question already. Let's open it
Hi
up.
there, on your left. So I'm totally new to this area, so my question might be C. I noticed there are two losses in your algorithm. The first one is the traditional loss, and the second one is the proposed one, right? But you haven't shown any results for using the proposed one, I mean the adversarial loss alone. How about remove that traditional one loss? And how much proportional to those kind of gradients? And also the second one, I noticed the experiments you conduct, I'm guessing you are using the synthetic data set. So also I noticed there are some real-world examples. Do you specifically train another model for realistic data, or you just use trained model and generalize on the real-world data?
Thank you for your question. For your first question, we also tried use only multi-view geometric loss and the adversarial loss for training the model. And the model seems to also have it could also have a reconstruction, a reasonable reconstruction result. But it may the points in the reconstruction model may not that it may seems good when evaluated with intersection over union, but it may not so good when evaluated with chamfer distance.
Okay.
And for your second question, what?
The second one is, do you have another model specifically trained on the real-world data sets or samples?
Okay. We just use the model trained on ShapeNet dataset for test on real-world images. Since we have some pre-processings for the real-world images, we first should mask the object to be reconstructed out, and maybe we should the object needed to be cropped or shifted to make sure that it locates in a proper location in the image plane, and then for sure we just make the real-world image similar to the images in the ShapeNet dataset training set, and use the model trained on ShapeNet to test to reconstruct the 3D model from the real-world image.
Okay, thank you.
Thank you.
Okay, I think we'll, in the interest of time, we'll move on. Let's thank Lee once again for the very nice talk.